substances, and I am going to get a shot of these guys on the messy, messy desk. And if you can't quite see the label on the beaker, it says NaCl. What's that rock? It's a chunk of salt. There's a salt mine about 1.5 miles underneath Lake Erie. And a number of years ago, I was lucky enough to get to go on a tour there. And it was all teachers and future teachers, educational professionals. And we were allowed to bring back samples. So I brought like a little Ziploc baggie. There was some guy who showed up with a full-on, like, 260 cubic inch backpack. And I should have, and I laughed at him when we got in the vans to go, and once we got down in the mine, I was incredibly jealous and wished that I had consulted him before we went, because I could have hauled out a lot more crystal than I did. But that's a chunk of salt. That is sodium chloride. There are salt deposits all over the planet. Sodium chloride is ubiquitous. It occurs everywhere in the environment. Any place that there was an old ocean, those salts tend to dry into geological layers, and you get big bands of salt. Doesn't matter if you take that sample from underneath Lake Erie, or you take it from the salt formations in Utah, if you take it from salt veins in the Black Rock Desert of Nevada, if you take it from a salt deposit in China, if you take it from a salt deposit in Siberia, it doesn't matter where you take it from, because it is a pure substance. It's going to have that, 800.7 degree Celsius melting point, no matter where it comes from. Because every sample of pure sodium chloride is going to have the same physical characteristics. Every sample of sodium chloride is going to have the same chemical characteristics. Every sample of sodium chloride is going to have one sodium ion for one chlorine ion, for one sodium ion, for one chlorine ion, come throughout the material. Doesn't matter where it comes from, it's a pure substance. It is reliable, it is dependable, steadfast and true. You should give it some sort of award. Any pure substance is like this. Now, sodium chloride is not an element, it's a compound. It's two elements put together, sodium and chloride, but it's still a pure substance. Whoops. I didn't mean to do that. We'll just do this. And the same could be said for any other pure substance. Like I said, water, acetic acid, if you have pure acetic acid, ethanol, any pure substance. No matter where you get it from, it's going to have the same composition, same characteristics. Great. Can't break that up physically. I cannot physically separate chlorine atoms from sodium atoms in this sample. Can't be done. However, if I have a mixture, I can physically separate it. And that's what you're going to do in your lab. So, when you are separating a mixture, the thing that you're always working on is difference. That's key. Is there has to be a difference in a physical characteristic to do a physical separation. So that difference could be appearance. You know, I said, give you a bowl of flour with chocolate chips in it, you can physically separate that manually based on appearance. Chocolate chips look different than flour. They have a different texture than flour. They have a different particle size than flour. You can pick them right out. If I gave you a bowl of flour with iron filings in it, there is a difference in magneticism. Iron filings are magnetically attracted. Flour is not. Again, that's a difference. You can you can differentiate things, you can separate things based on a difference in solubility. So how many of you have used the word soluble in your life? Ever? Okay, like, oh, that's soluble in blah, blah, blah. We very often when we generically refer to solubility, we're talking often about solubility in water. There are things that are soluble in other solvents, and we'll talk about solutions in chapter whatever down the road in the spring. Gasoline is a solvent. There are things that are soluble in gasoline that are not soluble in water. Grease and oil are not soluble in water. They are soluble in gasoline. They're soluble in a lot of sort of petrochemical cleaners. Gojo, if you've ever had grease on your hands and used Gojo, that is a solvent for greases. Water will not take grease off your hands. If you've ever gotten like Crisco or any kind of other greasy thing on your hands and tried to just wash it off with water, just rinse it, it doesn't work. Because those greases and fats are not soluble in water. So we can look at solubility in water, solubility in alcohol, solubility in gasoline, solubility in oil. We talk about things that are fat. You heard the distinction between fat-soluble and water-soluble vitamins. Anybody here take a vitamin every day? I just started. I'm trying to be really diligent about making sure I take a multivitamin every day. Water-soluble vitamins. Vitamin C is water-soluble. Guess what happens if you take too much vitamin C? You pee it right out. Your body just flushes it. Your pee turns bright yellow, and all the extra vitamin C is flushed out of your body. Vitamin D is fat-soluble. Guess what happens if you take too much vitamin D? Your body stores it. Guess where it stores it? Fatty tissue. So your body actually, because it's not water-soluble, your body can't flush it out with water. So these differences in solubility are one of the primary ways that we start to separate chemicals based on a physical. So that's a physical difference. Solubility is a physical characteristic, and you can see in the chemical database it's listed under physical characteristics. So let's do an example. If I have substance A, B, and C, and I'm looking at solubility in water. Okay, so I have these three substances all mixed together. We're assuming that we can't separate them magnetically, we can't separate them physically, we can't pick them apart. If I add water and stir, so I put these three things in a beaker. You did this on a small scale yesterday. What am I going to end up with? What will dissolve, what will not? Give me one thing. Tell you what, jot down, make a note to yourself, one thing that will dissolve, and then compare notes with your neighbor. Are you in agreement? Okay. All right. My front table here. Jaden and Alexa. Give me one thing that's going to dissolve.
I think sugar.
I don't see sugar on here.
I have salt.
I don't see salt on here. Okay, maybe I need to clarify the question. I have substance A, B, and C. Did you all?
Oh, okay. Oh, I pick A.
Okay. I like A. Did you all think it was something else?
Yes.
Was I asking you something else in your head? And okay. Failure to, what we have here is a failure to communicate. Couldn't eat hard-boiled eggs for a month. None of you know what I'm talking about, do you? Okay, so we're looking at substance A, B, and C, not random substances, because you know lots of substances that are soluble in water. That's good. Kool-Aid powder, yes, that's true. But not knowing what A, B, and C are, just any substance marked A, B, and C. I give you unknown substances, mix them together. If you add this mixture that you've been given to water, yeah, A is going to dissolve. Is B going to dissolve? Yeah. What about C?
No.
Chunks. Chunks! So you're going to have a clear solution with some chunks in it. What can you separate now? And how would you do this? How would you separate things based on solubility? You did this yesterday with sand and salt. Filter it. Run it through a filter. Mix it with water, run it through a filter. You can separate A and B from C. Can you separate A and B from one another? No. Because they're all mixed in the water. Again, what this comes down to is you cannot separate two things that have the same physical property. These are both soluble in water. They can't be separated using water. Now what if I add another column to this? Let's cut that. Okay. This is solubility in ethanol. So ethanol is hooch. Ethanol is the kind of alcohol that humans consume to become intoxicated. It's also a useful lab reagent for some things. We also use it in entomology labs to preserve insects. We preserve soft-bodied specimens in a 70% ethanol solution. That means we pickle our dead insects. We can use it as a solvent. Ethanol is a good solvent. So, looking at these, and I'll get rid of this, if we just think about solubility in ethanol, if we take this mixture that I've given you, we dump it in a beaker, we add ethanol, and we stir, what are you going to get? What's going to be dissolved and what will not be dissolved? A is going to be chunks. C is going to be chunks. B is going to be dissolved. What could we separate out in a filter this way?
A and C.
Yeah, we'd have A and C on a piece of filter paper, and we would have B in the water. Or in the, I'm sorry, we'd have B down in that ethanol solution. Once again, if they have the same solubility, we can't separate them. So separations are always based on a difference in physical characteristics, and these are physical separations. So let me ask you this as a brain, well, I won't get to the brain teaser yet. We can also do a separation based on heating, based on a difference in the heat of vaporization. So based on a difference in the temperature at which a substance goes from being a liquid to a vapor or a solid to a liquid, solid to a vapor. This is the principle used to separate out a lot of organic chemicals, including ethanol. So if you have a combination of ethanol and water, ethanol boils at, oh gosh, I want to say like 87 degrees Celsius, 90 degrees Celsius. What temperature does water vaporize at? 100. 100 Celsius. We're all in Celsius here. If you have a combination of ethanol and water. Oh, shoot. Okay. What I want you to do is this. I want you to attempt that flow chart on your own. When you come in tomorrow, we'll answer some questions on it. Closed toes, hair back, because we are going to start the lab tomorrow. You do need to summarize the procedures, that back page. It shouldn't take long. It's not a big procedure. Have a good day, folks.